Chapter 7, Section 9. Unlike the other sections in this chapter where you needed to learn one after another in order to do the final one and they all built on the other, this one is not that. However, what this section, the objective that I need you to understand in this section is things called endothermic and exothermic reactions. Now, this picture here shows an example of a thermite reaction. Now, thermite's pretty neat stuff, it's once you get this thing going, man, you can't get it to stop till it all runs out of the reactants. But getting it to go is actually pretty hard. Anyway, so that fact is, let me go to another slide here, is called, this activation energy. Some reactions, they don't take a whole lot of energy to get them going, and others do. But I want us to talk, let me go back here, and talk about what things happen to need to go and do for reactions to happen. First of all, 3 conditions for a reaction to occur are the following. Collision. You first got to get the reactants to collide together in order for them to be able to react. But they can't just collide together. They have to be oriented correctly. Their orientation needs to be aligned properly so that they can break and then recombine in other things to form bonds. But it's not just hitting, it's not just the correct orientation, but they have to have enough energy when they do collide in order to get over this little hump to make the reaction go. All right, let's proceed with exothermic. In an exothermic reaction, heat is released. So since heat is released, as we look at this diagram, you'll notice up here the energy of reactants is higher than down here, the energy of the products. Why? Because that energy that was inherently within the reactants is released and is gone. It's an exothermic reaction. So the energy of the products is less. And heat is considered a product. So when we write an equation, if I say, okay, designate this as an exothermic reaction, that means our energy is written on the right-hand side where the product is written. And you go, well, how do I know that this is energy? Well, back in some section that we learned about kilocalories, and we learned that those were units of energy. Now, an endothermic reaction is obviously just the opposite. So let's think about all of the things that would be opposite. Okay, what's the opposite of heat is released? Oh, heat is absorbed. What's the opposite of the energy of products is less than the energy of the reactants? Well, that would be the energy of the products would be more than the energy of the reactants. And heat, the opposite of heat is a product, would then be heat is a reactant. So let's look and see the table or diagram that would represent an endothermic reaction. Notice that the energy of our reactants is less than the energy of the products. Heat, and quite often don't think of heat as hot, think of heat as energy. Heat is absorbed, and so then when heat is absorbed from the surroundings, that means some of the energy from the surroundings are taken in. And when they are, this is the weird thing, is that then your product ends up being cooler. Now, so let's go back and say, in an endothermic reaction, heat is absorbed in from the surroundings, so it is written as a reactant because the energy is added to it. And so then, because of that, when we look here, this energy is greater than the energy over here. Heat is considered a reactant, and one more very important thing is the reaction feels cool. Whereas over here, in an exothermic reaction, the reaction quite often warms up or gets hot. The endothermic reaction, the reaction cools, gets cold. So now, let's look and see. Let's identify each reaction as endothermic or exothermic. Okay, so we look to see this Energy is on the product side, that means energy was released, so that's an exothermic reaction. This energy is on the reactant side, that means energy was absorbed, so that's endothermic reaction. And this last one, heat is released, that means that is an exothermic reaction.